what the Voyager saw in its 25 billion kilometer journey. A tiny metal emissary built in the 1970s is now over 25 billion kilometers away from Earth, traveling through the vast, silent void of interstellar space. How did we achieve this? And what does it mean to send something so far beyond home? Let's celebrate Voyager's milestone on today's episode. What does it mean to send a piece of humanity farther than anything has ever gone before? Voyager 1, a spacecraft launched over 4 decades ago, has traveled an astonishing 25 billion kilometers from Earth. It has left the boundaries of our solar system entirely, becoming humanity's first interstellar emissary. This isn't just a milestone in space exploration, it's a monumental achievement in human history. Voyager's journey began on September 5, 1977, when it launched from Cape Canaveral, Florida. It was designed as part of a bold mission, one that scientists and engineers called the Grand Tour. This once-in-a-lifetime opportunity arose from a rare planetary alignment, one that occurs only once every 176 years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were positioned in such a way that a single spacecraft could use their gravitational pulls as slingshots to propel itself from one planet to the next. This ingenious method, called a gravity assist, would save fuel and allow Voyager to explore multiple worlds in a single mission. The mission plan itself was incredibly ambitious. Voyager wasn't just meant to visit these distant planets. It was built to transform our understanding of them. At the time, the outer planets were little more than specks of light through Earth-based telescopes. We had no close-up images, no idea what their moons looked like, and only the faintest clues about their atmospheres or rings. Voyager was meant to change all that. Its mission was to provide humanity with its first detailed look at these faraway worlds. And it delivered spectacularly. In 1979, Voyager 1 reached Jupiter, the largest planet in the solar system. It gave us breathtaking images of its swirling storms, particularly the Great Red Spot, a hurricane-like storm larger than Earth that has been raging for centuries. Voyager also discovered that Jupiter's moons were not lifeless rocks, as many had assumed. One of its moons, Io, turned out to be the most volcanically active body in the solar system, with massive plumes of sulfur erupting from its surface. Just a year later, in 1980, Voyager reached Saturn. For the first time, we saw the intricate details of its iconic rings made of countless particles of ice and rock, shaped by the gravitational influence of Saturn's many moons. Voyager also revealed the mysteries of Titan, Saturn's largest moon. Titan's thick orange atmosphere hinted at the possibility of liquid hydrocarbons on its surface, raising new questions about whether such an environment could support life. Though Voyager 1's primary mission ended after its encounter with Jupiter and Saturn, its journey was far from over. In 1990, it completed one final task before turning its cameras off for good. It captured the iconic pale blue dot photograph. From a distance of 6 billion kilometers, Voyager 1 looked back at Earth and snapped an image of our planet as a tiny speck suspended in the vastness of space. That photograph, a single pixel in size, would become one of the most famous images ever taken, a humbling reminder of just how small and fragile our world truly is. After that, Voyager 1 continued its journey outward, eventually reaching the edge of the solar system. This boundary, known as the heliopause, marks the point where the solar wind, the stream of charged particles flowing from the Sun, meets the interstellar medium, the space between stars. In 2012, it crossed this boundary, becoming the first human-made object to enter interstellar space. This was a historic moment. For the first time, something created by human hands had left our solar system and ventured into the vast unknown of the galaxy. But what makes Voyager's journey so remarkable isn't just the distance it has traveled. It's the fact that it's still operational. Remember, this spacecraft was built in the 1970s, with technology that's laughably outdated by today's standards. Its onboard computers have less memory than a modern smartphone, and its instruments were designed to last only 5 years. Yet, through a combination of ingenious engineering and careful management, Voyager has far outlived its original mission. How does it keep going? The power source of this machine is a radioisotope thermoelectric generator, or RTG, which converts the heat from decaying plutonium into electricity. Over the years, the amount of power it generates has decreased, forcing engineers to shut down non-essential systems to conserve energy. Despite these limitations, Voyager has continued to send back valuable data, providing insights into the nature of interstellar space. Voyager's endurance is a triumph of both engineering and science. It's a reminder of what humans can accomplish when we combine creativity, ingenuity, and a relentless desire to explore. This spacecraft, launched during the height of the Cold War, has become a symbol of unity and curiosity, carrying a message from Earth to the stars. And that's the other part of the mission, the part that isn't about science, but about humanity. Attached to the spacecraft is the Golden Record, a time capsule containing sounds, images, and music from Earth. It's a message to any intelligent life that might one day find Voyager, a way of saying, this is who we are, this is where we come from. The Golden Record is a testament to our optimism and a belief that even in the vast emptiness of space, there might be someone or something out there to receive our message. As we celebrate 25 billion kilometers traveled in Voyager's ongoing journey into interstellar space, it's worth reflecting on what it represents. It's not just a piece of machinery drifting through the void. It's a symbol of human curiosity, resilience, and hope. Voyager is proof that when we push the boundaries of what's possible, we can achieve things that are truly extraordinary. The first stop in Voyager 1's billion-kilometer adventure was Jupiter, which it first reached in 1979. By that time, it was like opening a door to a world we had only glimpsed through the hazy lens of telescopes. For centuries, Jupiter had been a distant enigma, a colossal gas giant with swirling clouds and 4 bright moons first noticed by Galileo. But Voyager's close-up views transformed those specks of light into vibrant, dynamic worlds, each with its own story, and revealed Jupiter itself to be far more complex than anyone had imagined. The first thing that struck scientists was Jupiter's atmosphere, a chaotic canvas of swirling storm systems and alternating bands of dark and light clouds. Voyager's images revealed the intricate details of the Great Red Spot, a storm so massive that it could fit 3 Earths inside. This hurricane-like vortex wasn't just a feature of Jupiter's weather. It was a centuries-old tempest, with winds tearing across its surface at hundreds of kilometers per hour. Surrounding the Great Red Spot were countless other storms and swirling eddies, some of them only visible because of Voyager's unprecedented resolution. Jupiter's atmosphere wasn't just a swirling gas giant. It was a living, breathing system of unimaginable scale and complexity. But Jupiter's surprises extended beyond its atmosphere. Voyager discovered something completely unexpected, a faint ring system encircling the planet. Until then, rings had been thought to be unique to Saturn, but what's revealed is that Jupiter too had rings, though much thinner and darker than Saturn's iconic bands. These faint rings are composed of tiny dust particles, likely created by meteoroid impacts on Jupiter's small inner moons. While they may not be as visually striking as Saturn's, Jupiter's rings were a crucial discovery, showing that these features are more common among giant planets than previously thought. The most groundbreaking revelations, however, came not from Jupiter itself, but from its moons, especially the 4 largest, known as the Galilean moons. Each of these worlds turned out to be a universe unto itself, full of surprises that scientists are still grappling with today. First, there was Io, the innermost of the Galilean moons. The close-up images of Io astonished scientists. Instead of a cold, cratered surface like Earth's moon, Io was revealed to be a world of fire and fury. Voyager captured erupting volcanoes, shooting plumes of sulfur hundreds of kilometers into space. This was the first time geological activity had been observed beyond Earth, and it completely upended assumptions about moons being geologically dead. Io's intense volcanic activity is driven by tidal forces, The gravitational push and pull from Jupiter and its neighboring moons stretches and squeezes Io, generating immense heat in its interior. The result is a constantly reshaping surface, painted in vivid yellows, oranges, and reds by sulfur and volcanic rock. Then there was Europa, a moon that quickly became one of the most intriguing objects in the solar system. Voyager's images showed a bright, icy surface, crisscrossed by dark lines and ridges. These features hinted at something extraordinary: the possibility of a subsurface ocean beneath Europa's frozen crust. Scientists theorize that, like Io, Europa experiences tidal heating from Jupiter's gravitational pull, but instead of driving volcanism, this heat keeps water beneath the ice in a liquid state. If true, this would make Europa one of the most promising places in the solar system to search for life. Voyager couldn't directly confirm the presence of this ocean, but its observations set the stage for future missions to investigate Europa in greater detail. Next was Ganymede, the largest moon in the solar system, bigger even than Mercury. Voyager revealed Ganymede to be a fascinating mix of old and new. Its surface is a patchwork of ancient, heavily cratered regions and younger, smoother areas, suggesting that some parts of the moon have been reshaped by geological processes. Even more intriguingly, Voyager's instruments detected evidence of a magnetic field around Ganymede, the first time a moon was found to have its own magnetosphere. This discovery raised questions about Ganymede's internal structure and hinted at the possibility of a liquid metallic core generating the field, an exciting parallel to Earth's own magnetic field. Finally, there was Callisto, the outermost of the Galilean moons. Callisto's surface was revealed to be one of the oldest and most heavily cratered in the solar system, a frozen record of billions of years of impacts. But even Callisto held surprises. Voyager's data hinted at a layer of liquid water deep beneath its icy crust, making it yet another candidate for harboring a subsurface ocean. Callisto's relatively inactive surface stands in stark contrast to the volcanic chaos of Io or the icy dynamism of Europa, but its potential for hidden water has kept it in the spotlight for astrobiologists. Together, these four moons shattered our understanding of what moons could be. Before Voyager, moons were thought to be lifeless, inert rocks, but the spacecraft revealed them to be dynamic, geologically active worlds, each with its own unique characteristics. From Io's fiery volcanoes to Europa's potential ocean, Ganymede's magnetic field, and Callisto's ancient ice, the Galilean moons painted a picture of a solar system far more diverse and complex than we ever imagined. Voyager's discoveries at Jupiter also deepened our understanding of the planet's immense magnetosphere, a region of space dominated by its magnetic field. Jupiter's magnetosphere is the largest structure in the solar system, stretching millions of kilometers into space and interacting with its moons in fascinating ways. For example, Io's volcanic activity is directly influenced by its interaction with Jupiter's magnetic field, which strips particles from Io's eruptions and creates a glowing plasma torus around the planet. The data collected at Jupiter didn't just transform our understanding of the planet and its moons, it also laid the groundwork for future missions. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, built on Voyager's discoveries, providing more detailed studies of its moons and magnetosphere. And today, missions like the Europa Clipper, set to launch in the 2030s, aim to explore the tantalizing potential of Europa's hidden ocean in the search for extraterrestrial life. Voyager's time at Jupiter was a turning point in the history of space exploration. It revealed a system of worlds as vibrant and diverse as the planets themselves, and it showed us that even the moons of a distant gas giant could hold secrets that challenge our understanding of the universe. As Voyager left Jupiter and continued on to Saturn, it carried with it not just images and data, but a legacy of discovery that continues to inspire new questions and new missions to this day. When Voyager 1 arrived at Saturn in November of 1980, it was entering the realm of one of the most visually stunning objects in the solar system. Saturn's rings had fascinated astronomers for centuries, but the images from the transmission revealed them in breathtaking detail. uncovering secrets that were hidden to even the most powerful telescopes on Earth. From the planet itself to its mysterious moons, Saturn turned out to be a treasure trove of discoveries that continue to inspire exploration today. The first thing Voyager focused on was Saturn's intricate ring system. From Earth, Saturn's rings look like a single continuous structure, but it was revealed that they are composed of thousands of individual ringlets, each made up of countless particles of ice and rock. These particles range in size from tiny grains of dust to boulders the size of houses, and they're constantly in motion, colliding and interacting in a delicate gravitational dance. Voyager's data show that Saturn's rings are dynamic rather than static, shaped and sculpted by the gravitational influence of the planet's shepherd moons, small moons that either orbit within the rings or just beyond them. These moons act like cosmic sculptors, clearing gaps, creating waves, and maintaining the structure of the rings. One of the most famous gaps in the rings is the Cassini division, a dark region separating the A and B rings. Voyager's observations help scientists understand that this gap isn't empty. It's filled with smaller particles that are faint and difficult to see. It also discovered radial features within the rings called spokes, dark streaks that seem to defy explanation at the time. These spokes, scientists now believe, are caused by interactions between Saturn's magnetic field and the tiny particles within the rings. As stunning as the rings were, Saturn's moons proved to be just as remarkable, beginning with Titan, the second largest moon in the solar system and one of Voyager's most exciting discoveries. Titan was shrouded in a thick orange haze that we were able to penetrate, revealing an atmosphere unlike anything else in the solar system. Titan's atmosphere is rich in nitrogen and contains traces of methane and other hydrocarbons, making it strikingly similar to what scientists believe Earth's atmosphere might have been like billions of years ago before life evolved. Titan's atmosphere raised profound questions about its potential for astrobiology. Could its surface or its atmosphere harbor the building blocks for life? Voyager couldn't see through the haze to determine exactly what lay on Titan's surface, but its data suggested the possibility of lakes or seas of liquid methane and ethane, a phenomenon that would later be confirmed by the Cassini-Huygens mission. Titan quickly became one of the most intriguing moons in the solar system, a place scientists dreamed of exploring further. If you could send a spacecraft to study just one world in the Saturn system, would you choose Titan with its mysterious atmosphere and potential lakes, or Enceladus with its icy plumes and subsurface ocean? Let us know your pick in the comments below. Speaking of Enceladus, Voyager's observations of this small icy moon hinted at something extraordinary. Its surface was one of the brightest and most reflective in the solar system, indicating that it was covered in fresh, clean ice. This was already unusual, but the data suggested there might be more going on beneath the surface. Though it couldn't confirm it at the time, later missions like Cassini would discover that Enceladus is home to geysers of water vapor shooting out from cracks in its icy crust. These plumes contain organic compounds and hint at a subsurface ocean, making Enceladus one of the most exciting places to search for extraterrestrial life. Voyager's early observations laid the groundwork for these discoveries, turning this tiny moon into a major target for astrobiology. Saturn's magnetic field also turned out to be a fascinating feature of the planet's system. Voyager found that the magnetic field was both powerful and unique, perfectly aligned with Saturn's axis of rotation, a phenomenon scientists still don't fully understand. This magnetic field extends far beyond the planet itself, interacting with the rings and moons in complex ways. For example, the magnetic field influences the particles in the rings, creating the mysterious spokes. It also creates auroras at Saturn's poles, similar to the northern and southern lights we see on Earth. And then there were Saturn's other less famous moons, each of them unique in its own way. Take Mimas, for example, a small cratered moon that Voyager revealed to have a massive impact crater dominating its surface. This crater, named Herschel, is so large relative to the size of the moon that it makes Mimas look like the Death Star from Star Wars. Then there's Iapetus, a moon with one of the strangest appearances in the solar system. One side is bright and reflective, while the other is dark and coated in what appears to be a layer of carbon-rich material. Voyager's observations of these two moons raised questions that still puzzle scientists today. What caused Iapetus's stark two-tone coloration? How did Mimas survive the impact that created the Herschel crater? From its majestic rings to its diverse collection of moons, Voyager revealed Saturn as a dynamic, complex system full of surprises. Its discoveries didn't just change how we viewed Saturn, they inspired new questions and future missions. The Cassini spacecraft, which arrived at Saturn in 2004, was a direct successor to Voyager, building on its discoveries and diving deeper into the mysteries of Titan, Enceladus, and the rings. Even today, Saturn remains one of the most intriguing destinations in the solar system, and it's all thanks to the little probe's trailblazing work. As Voyager left Saturn and continued its journey outward, it carried with it the knowledge of everything it had uncovered. Saturn, with its shimmering rings and fascinating moons, was no longer just a distant jewel in the night sky. It was a living system, full of beauty, complexity, and the raw potential for life. The Space Explorer didn't just explore Saturn, it introduced us to an entirely new way of seeing our place in the universe. After its historic encounters with Jupiter and Saturn, Voyager 2 continued its epic journey to explore the farthest reaches of the solar system, becoming the first spacecraft to visit Uranus and Neptune. These icy giants, distant and mysterious, were worlds we knew almost nothing about. Its flybys in the 1980s gave humanity its first close-up look at these distant planets, revealing strange and unexpected phenomena that challenged our understanding of the outer solar system. First up was Uranus, which Voyager 2 visited in January of 1986. Uranus had always stood out in the solar system because of its extreme axial tilt. It essentially orbits the Sun while laying on its side, with its poles nearly where most planets' equators would be. This unusual tilt results in extreme seasons that last for decades, with one pole facing the Sun for half a Uranian year, about 42 Earth years, before plunging into complete darkness for the other half. Voyager's observations helped us understand how this tilt affects the planet's atmosphere and weather. One of the most surprising discoveries at Uranus was its magnetic field, which turned out to be just as strange as the planet's tilt. Unlike Earth's magnetic field, which is roughly aligned with our rotational axis, the magnetic field of Uranus is widely off-center and tilted at a bizarre angle, almost as if it were lopsided. This irregular magnetic field suggested that the planet's interior structure was more complex than previously thought, with layers of conducting material generating the field in unexpected ways. Voyager also revealed the faint ring system of Uranus, which, unlike Jupiter's rings, had been invisible from Earth. These dark, narrow rings were a surprise, showing that rings are not exclusive to Saturn, but are a more common feature of the outer planets. Voyager's data also hinted at the existence of shepherd moons, small moons that help maintain the structure of the rings through their gravitational influence. Moving beyond Uranus, Voyager 2 arrived at Neptune in August of 1989, giving us our first close look at the farthest planet in the solar system. Neptune was a world of striking blue hues, its vivid color the result of methane in its atmosphere. But what shocked scientists the most was the discovery of an enormous storm system, which they named the Great Dark Spot. This storm, similar to Jupiter's Great Red Spot, was a massive swirling vortex of high-speed winds. In fact, Neptune's winds turned out to be the fastest in the solar system, reaching speeds of up to 2,100 kilometers per hour. Neptune's dynamic atmosphere and extreme weather were astonishing given its distance from the Sun. How could a planet so far from the Sun, receiving so little energy, generate such powerful storms? Voyager's observations raised more questions than answers, challenging our understanding of planetary atmospheres and energy sources. And then there was Triton, Neptune's largest moon, which quickly became one of the most intriguing objects Voyager encountered. Triton turned out to be a world of icy mysteries, with a surface that was young and geologically active. Voyager captured evidence of cryovolcanism, ice volcanoes that erupted liquid nitrogen instead of molten rock, and even detected nitrogen geysers, shooting plumes of gas and particles into space. What made Triton even more fascinating was its retrograde orbit. It circles Neptune in an opposite direction of the planet's rotation. This unusual orbit suggests that Triton was likely a captured object, possibly a former dwarf planet that Neptune's gravity pulled into its orbit. Triton's strange characteristics raised tantalizing questions about its origins and the processes shaping icy worlds at the edge of the solar system. Voyager's flybys of Uranus and Neptune also confirmed that these planets, like Jupiter and Saturn, have ring systems, though they are faint and difficult to detect. The rings of Uranus and Neptune are composed of dark, icy particles, and their existence was a crucial finding. It showed that rings are not a rare phenomenon, but a recurring feature among the giant planets, each with its own unique characteristics. With its encounters at Neptune complete, Voyager 2 became the last human-made object to visit a planet in the solar system. But the mission was far from over. Both Voyager 1 and 2 continued their journeys outward, heading towards the edge of the solar system and beyond. This boundary, known as the heliosphere, marks the point where the sun's influence ends and interstellar space begins. The heliosphere is created by the solar wind, a stream of charged particles flowing outward from the sun. As the Voyagers approached the edge of the heliosphere, they began to detect changes in the environment around them. The solar wind weakened, giving way to the interstellar medium, the matter and radiation that exists between stars. In 2012, Voyager 1 became the first spacecraft to cross the heliopause, the boundary between the heliosphere and interstellar space. Voyager 2 followed in 2018. These crossings were monumental achievements, marking the first time human-made objects had entered the vast, uncharted territory between the stars. Voyager's instruments, even after decades of operation, continued to send back data about this transition zone, revealing new details about the nature of interstellar space and the protective bubble created by our sun. Voyager's interstellar journey isn't just a scientific milestone, it's a profound moment in human history. These spacecraft, launched in the late 1970s with technology far less advanced than the smartphone in your pocket, have traveled farther than anyone ever thought possible. They are now silent emissaries carrying the golden record, a message from Earth to any intelligent life that might one day find them. As our metallic adventurers continue their journey into interstellar space, they remind us of the boundless curiosity and ingenuity that drive humanity to explore. From the tilted magnetic field and faint rings of Uranus to Neptune's raging storms and Triton's icy geysers, Voyager revealed worlds we had never seen before. It showed us that even at the farthest edges of the solar system, there is much to discover and much to inspire. When Voyager launched in 1977, it carried more than just scientific instruments and cameras. It carried a message, one crafted not just for the present, but for eternity. Tucked aboard each Voyager spacecraft is the Golden Record, a literal time capsule of humanity, designed to tell the story of who we are to anyone or anything that might one day find it. It's a message of peace, curiosity, and hope, and its creation is just as extraordinary as the mission itself. The idea of the Golden Record was the brainchild of famed astrophysicist Carl Sagan and his team, who were tasked with deciding what this cosmic message should contain. But how do you sum up the entirety of human existence on a record that's only 12 inches across? What would you include if you had to represent not just science, but art, culture, and the essence of humanity? Sagan and his team faced these questions as they curated the Golden Record, and their choices reflect an astonishingly optimistic view of what humanity could be. The record itself is a gold-plated copper disc designed to last for billions of years in the harsh conditions of space. It contains sounds, images, music, and greetings from Earth, encoded in both analog and digital formats. The idea was that if an intelligent extraterrestrial civilization were to find Voyager, they could decode the contents of the record and learn about life on Earth. To help them, the record even includes instructions etched onto its surface on how to play it. So what's exactly on the golden record? First, there are the sounds of Earth, the natural symphony of our planet. It includes the crackling of thunder, the murmur of waves on a shore, the chirping of birds, and the laughter of a baby. These sounds were chosen to convey the diversity and beauty of life on Earth, from the elemental forces of nature to the intimate moments of human experience. Then there are the greetings, recorded in 55 different languages. They range from ancient languages like Akkadian, spoken over 6,000 years ago, to modern tongues like English, Chinese, and Swahili. Some of the greetings are formal, like the English message, "Hello from the children of planet Earth." Others are poetic, like the Arabic greeting, which translates to "Peace be upon you." Together, they represent humanity's desire to communicate across space and time, to connect with whatever might be out there. And of course, there is music, a universal language that transcends cultural boundaries. The golden record contains 27 musical tracks, carefully chosen to represent the wide spectrum of human creativity. It includes classical masterpieces like Bach's Brandenburg Concerto and Beethoven's Fifth Symphony, as well as traditional music from around the world. There's a Navajo night chant, a Peruvian wedding song, and even a recording of Chuck Berry's Johnny Be Good, a nod to the energy and innovation of rock and roll. But the golden record isn't just about sounds. It also contains images encoded as analog signals that can be decoded into 116 photographs. These images depict life on Earth in all its variety. People from different cultures, animals in their natural habitats, diagrams of human anatomy, and even mathematical equations. The goal was to show not just what humans look like, but how we think, how we live, and how we see the universe. The golden record is more than just a technical achievement. It's a philosophical statement. It reflects humanity's deep curiosity and our desire to connect with something greater than ourselves. By sending this message into the cosmos, we're acknowledging the vastness of the universe and our tiny place within it. But at the same time, we're asserting that our existence matters, that our story is worth telling even if no one ever hears it. For Carl Sagan, the golden record was an act of profound optimism. In his words, "The launching of this bottle into the cosmic ocean says something very hopeful about life on this planet." It's a declaration that, despite our flaws and struggles, we are capable of creating beauty, of reaching out to the unknown, and of imagining a future where we are not alone. The cultural and philosophical significance of the golden record goes far beyond the Voyager mission. It challenges us to think about who we are as a species and how we want to be remembered. What does it mean to send the message that might outlive not just our civilization but our planet? What does it say about us that we would try? The golden record is in many ways a mirror. It reflects our hopes, our fears, and our aspirations, and it asks us to consider how we might look to an outsider. Even today, the golden record continues to inspire. It's a reminder that space exploration isn't just about science, it's about storytelling. It's about asking the biggest questions. Where do we come from? Are we alone? What does it mean to be human? The record itself has become a cultural icon, referenced in movies, books, and music. It's a symbol of our collective curiosity and our belief in the power of communication, even across unimaginable distances. As Voyager drifts farther and farther from Earth, the golden record remains its most poignant legacy. Long after its instruments have fallen silent, Voyager will continue its journey through the stars, carrying our message with it. In billions of years, when the sun has burned out and Earth is no more, Voyager and the golden record will still be out there. It's humbling to think that this tiny spacecraft, built with 1970s technology, might be the only trace of humanity that survives the passage of time. Truly enough, the golden record is more than a message to extraterrestrials. It's a message to ourselves. It reminds us of what we're capable of when we dare to dream. It's a testament to our creativity, our resilience, and our unshakable curiosity. And as long as Voyager continues its journey, that message will endure, carrying our story into the cosmos. As Voyager drifts farther and farther from Earth, its legacy continues to ripple across the fields of science, engineering, and philosophy. It's more than just a spacecraft. It is a symbol of humanity's relentless curiosity and ingenuity. What Voyager achieved, and what it continues to inspire, has shaped how we explore the cosmos today, and how we dream of doing so tomorrow. One of Voyager's most profound contributions has been its impact on modern planetary science. The discoveries it made at Jupiter, Saturn, Uranus, and Neptune set the stage for the missions that followed. Without Voyager, there may have been no Galileo spacecraft to orbit Jupiter, no Cassini mission to Saturn, and no ongoing plans to return to these distant worlds. For example, Voyager's tantalizing glimpse of Europa's icy surface and hints of a subsurface ocean sparked decades of speculation about the Moon's potential for harboring life. That spark has now become the Europa Clipper mission, set to launch in the 2030s, which will study Europa in unprecedented detail. Titan, with its thick atmosphere and possible methane lakes, was another revelation of the Voyager mission. That discovery inspired the Cassini-Huygens mission, which confirmed the existence of liquid hydrocarbon seas on Titan's surface. And now, we're preparing to send a drone-like lander called Dragonfly to this mysterious moon. Dragonfly will explore Titan's surface and atmosphere, searching for the chemical precursors to life. These missions, and many more, owe their existence to the groundwork Voyager laid decades ago. But Voyager's influence isn't limited to the planets and their moons. Its journey beyond the solar system has also revolutionized our understanding of the heliosphere, the vast bubble of charged particles and magnetic fields created by the Sun. Before Voyager, scientists could only theorize about what lay beyond the heliosphere's boundary. Voyager 1 crossed the heliopause, the edge of the heliosphere, on August 25, 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed suit in 2018. These crossings were monumental achievements. Voyager's instruments revealed how the solar wind interacts with the interstellar medium, the thin soup of gas and dust that fills the space between stars. It showed us that the heliosphere acts as kind of a protective shield, deflecting much of the cosmic radiation that bombards the galaxy. The data Voyager continues to send back from interstellar space is invaluable, giving us a glimpse of what lies beyond the Sun's influence and helping us understand the environment future interstellar missions might face. Voyager's endurance as a spacecraft is nothing short of an engineering marvel. Remember, this mission was designed in the 1970s, with technology that predates the internet and modern personal computers. Its systems were built to last only 5 years, just long enough to complete its primary mission to study Jupiter and Saturn. Yet, here we are, nearly 5 decades later, and Voyager is still going. How has it lasted so long? The answer lies in its design. Voyager is powered by a radioisotope thermoelectric generator, RTG, which converts the heat from decaying plutonium into electricity. While the power output has gradually diminished over the years, Voyager's team of engineers has managed to keep the spacecraft operational by shutting down non-essential systems and carefully rationing its remaining energy. Voyager is now running on only a fraction of its original instruments, but it continues to send back data even from billions of kilometers away. This longevity speaks to the brilliance of the engineers who built it and the dedication of the team that still manages it today. The fact that Voyager can operate autonomously, navigating the vast emptiness of space without human intervention, is a testament to the ingenuity and ambition of those who dared to send it on its journey. And then there is the pale blue dot, perhaps its most iconic contribution to humanity's perspective on itself. In 1990, as Voyager 1 was preparing to turn off its cameras to conserve energy, Carl Sagan convinced NASA to turn the spacecraft around for one final photograph. From a distance of 6 billion kilometers, Voyager captured an image of Earth, a tiny speck of light, barely visible against the vast darkness of space. That image, the pale blue dot, is more than a photograph. It's a symbol of humility, a reminder of the fragility of our world. In Sagan's words, look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives. The pale blue dot challenges us to see ourselves from a cosmic perspective, to recognize that our differences are trivial in the face of the vastness of the universe. As Voyager continues its journey, it also carries with it the golden record, a message to the stars that encapsulates the essence of who we are as a species. Voyager's future is silent and solitary. Its power will eventually run out, and it will no longer be able to communicate with Earth. But even then, it will keep traveling. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Callisto 445. Long after humanity is gone, long after Earth itself has ceased to exist, Voyager will still be out there, a silent wanderer in the galaxy. It's humbling to think that this tiny spacecraft, no larger than a small car, may someday be the only trace of humanity left in the cosmos. Voyager is a testament to what we can achieve when we dare to dream big, to push the boundaries of what's possible. It's a reminder that even in the vast emptiness of space, we can leave a mark. As we celebrate everything Voyager has accomplished, we also look to the future. What will the next Voyager be? Will we one day send a spacecraft to another star? Will it carry a new message, a new story of humanity? Share this video, your thoughts in the comments, and as always, stay insanely curious.